Dear students, welcome and thank you for tuning in to this video with me, Dr. Loay Al-Zube. We are still talking about the kinematics of a particle moving on a curved line as part of the statics and dynamics course. So in this video, I'm going to solve a problem in which we are going to relate kinematics quantities in terms of the rectilinear components of a vector. And in the following lecture videos, we're going to talk about more about, you will do more examples about the particle moving on a curved path. But we would like to make sure that we understand how can we get kinematics quantities from rectangular components of vectors. And so the problem that we are going to solve is this. We have a box that is sliding down a slope and described by this equation. And let me just change the color of my pen so that it is clear. Yeah, okay. So for this example again, so we have a box that slides down a slope, and we have this equation that's y equals 0.05 x squared meters. Please note that this is I'm doing green. That's good. So this is my governing formula. I have the y component of the y position is a function of x. And we know that we are changing with respect to time, right? So we need to do something called partial derivatives. So keep in mind, y is a function of x and x is a function of time, because we need to move, and if we are moving, we're moving with respect to time. So you need to keep that in mind, and I will do something like this to simplify the process more. So let me use red. I will say that y actually y equals 0.05 x of t square. So this will give us a clear understanding of what we are doing. So I have my y is a function of x, where x is a function of time. You need to keep that in your mind. And x is in meters. And then the question is giving us that we have the x component of the velocity equal to minus 3 meters per second, and the a component of in the x direction is minus 1.5 meters per second at x equals 5 meters, when x equals to 5 meters. We need to keep that in mind, and I'm going to show you what does that mean and why this is important. So the question now is, can you find the y component of the velocity and acceleration of the box at x equals 5? So can I find, again, the y component of the velocity and acceleration? So can I find Vy and Ay? I was given Vx and Ax. Can I find Vy and Ay? That's the question. Note that the particle velocity can be found by taking the first derivative. We know that. Everybody knows that the velocity is the first derivative of the position. However, you need to keep in mind if if one of the variable is a function of another variable, and which one is function of time. That's very important. And the acceleration can be found by taking the second derivative. So if you have position, I will derive it first one time, that's velocity, derive it again, that's acceleration. And we will take the derivative of the position to find the components of the acceleration. That's our plan. So how are we going to do this? Step one, if you want to find the velocity, so v is going to be the derivative of position. If I'm interested in the y component of velocity, I'm going to do y dot, right? And if you want to, this is the function that we have. Y is 0.05 x squared. If I want to derive this, I will say that y dot is equals, this is x to the power 2. So you put 2 in for the derivative at the beginning, you multiply it with the constant, and then you take x and you subtract 1 from the power, that's x. Remember, we need to have x dot as well, because x is a function of time. And if you recall the partial derivatives, this is how we do it. So, quick recall. This is y is a function of x, so y dot is going to be 2 multiplied by the constant 0.05, and then you have x, because that's how we do the derivative, and then you need to derive x itself, so that's x dot, right? And this is how you find the position, the velocity in the y direction. So if you multiply 2 with 0.05, this is what you end up with. We did this partial derivative because x is a function of time. So you derive x first by itself, and then you need to derive x with respect to time, and you put it x dot. Same thing goes for the acceleration. Now, since we have the velocity, which is 0.01 x dot, now I have this y dot, which is the velocity, is a function that is a multiplication of two functions. One of them is x and one of them is x dot, and both of them are functions of time. If you recall from calculus, when you do the derivative, if I want to do the acceleration, which is the second derivative of y double dot, I need to do the derivative of the multiplication of two functions, and that derivative is the first multiplied with the derivative of the second, plus the second multiplied with the derivative of the first, and that's what we're doing. So 0.01, that's a constant, goes down, so this is x dot multiplied with the derivative of x, that's x dot multiplied by x dot, plus 0.01, that's the constant, and then you have the second multiplied with the derivative of the first, that's x multiplied by x double dot, that's acceleration. Again, we are doing this partial derivatives because x and x dot and x double dot are all functions of time, so I have to do this partial derivative. And then after having these two formulas, this one and the other one there, that's 2, so this is 1 and that's 2, we can now substitute with the values that were given to find the y components by substituting what the x components that the question gave us. So recall that the question gave us that the vx, the velocity in the x-axis is minus 3 meters per second, and that's, if this is vx, that's x dot actually, right? Ax, it was given minus 1.5, that's x double dot, and we can now substitute to find the velocity in the y direction. So that's vy going to be y dot. Recall that we have it from the previous equation, 0.1 x dot. You substitute 0.1, x is 5 because that's where we want to calculate our values, and x dot, that's vx actually, that's minus 3, and this is your value. The y double dot, again from the previous slide, that's the equation that we come up with because it's the multiplication of two functions. You have x dot and x dot, that's minus 3 multiplied by minus 3, x multiplied by x double dot, that's acceleration, which is 5, and then you get your y double dot, and that's ay. So at x equals 5 meters, you can say that vy is minus 1.5, ay is 0.15. You can add directions. So for the velocity, since it's negative, it means that a is going to the down in your Cartesian coordinate system. Ay is positive. You can put it up, but ay, it means that if it's positive, we are accelerating, and that's all in the y direction. That's what it does mean. It doesn't mean that anything about the position, but it says that we are accelerating in the y direction. I hope that this question was clear and you got a good understanding of what does it mean to do derivatives of positions that they are functions of time, and how can a question could come up, and what are the steps that we need to identify. So step 1, make sure that you know what is your function that describing the motion. Step 2, when you make the derivative with respect to time, how do you do partial derivatives, and 3, how to substitute the values to get what you are asked to identify. Thank you for watching. Until the next video. Bye.